All right, you got the notes for section 9.3, which deals with relative rates of growth. So comparing rates of growth, faster, slower, the same rate of growth as x approaches infinity. So let f of x and g of x be positive for x sufficiently large. So once x gets big enough, they both stay positive. F grows faster than g, or vice versa, g grows slower than f as x approaches infinity if the limit of f over g is infinity or g over f is 0. So if you get infinity, that means the top one grows faster. If you get 0, it means the bottom function grows faster. They grow at the same rate if, when you do the limit, you get some number L that's not 0. So any other value except for will be positive because we're going positive here. All right, so example 1 says show the function e of x grows faster than x squared as x approaches infinity. So we got the limit as x approaches infinity, so e to the x over x squared. Well, if we try to do this, we get e to the infinite over infinity squared, which is infinity over infinity. So can't do that, so L'Hopital's rule. So the derivative of e to the x is e to the x. The derivative of x squared is 2x, so try again. E to the infinity over 2 times infinity, so still infinity over infinity. So L'Hopital again. Limit as x approaches infinity of e to the x over 2, which is now e to the infinity over 2, which is infinity over 2, which is infinity. So the top function grows faster. Okay, so show that ln x grows slower than x and x squared. So that means that if we put ln x on the bottom, we should get 0. So for part A, the limit as x approaches infinity of x over ln x. Well, if we try this, we get infinity over infinity, which can't be done, so L'Hopital's. So the 1 over x. So this is the same thing as the limit as x approaches infinity of just x, which is infinity, which means the top function grows faster, which means the bottom function grows slower. So for B, limit as x approaches infinity of x squared over ln x, which would be infinity squared, whoops, not even on the screen, over infinity, which is, so L'Hopital, so 2x over 1 over x, which is the same thing as 2x squared, which is 2 times infinity squared or infinity. So the top function grows faster than the bottom function. All right, example 3. Show that x grows at the same rate as x plus sine x. So to grow at the same rate, that means that when we do this, oops, we have to get a non-zero number. So if we try this right now, we'll get infinity over infinity. So we have to L'Hopital it. So limit as x approaches infinity. So the derivative of the top is 1, the derivative of the bottom is cosine x. Now, the issue here is we can't technically evaluate this, but the cosine of x will always be between 1 and -1. So this is going to be some number. If we try it the other way, if we put the x plus sine x on top, this is the same thing as 1 plus sine x over x. So, and this does equal 1. So you get a non-zero number. All right, so example 4, let a and b be numbers greater than 1. Show that log base a of x and log base b of x grow at the same rate as x goes to infinity. So the limit as x goes to infinity log base a of x over log base b of x. So actually we're going to do a trick, we're going to do the change of base. So log base a of x is the same thing as the natural log of x divided by the natural log of a. And the bottom down here, that's the natural log of x divided by the natural log of b. And if you work this out, this actually becomes, we're actually going to flip this guy over and multiply. So here we'll write it down. Limit as x approaches infinity of ln x over ln a times ln b over ln x. So you flip the bottom fraction multiply. So these guys cancel. So this just equals the natural log of b divided by the natural log of a, which is going to be some number because a and b are numbers. So this equals some value, so they grow at the same rate. All right, transitivity of growing rates. If f grows at the same rate as g as x goes to infinity, and g grows at the same rate of h, then f grows at the same rate of h. So we can kind of like the transitive property of a is equal to b and b is equal to c, then they are equal to each other. So show that f of x equals root x squared plus 5, and g of x grow at the same rate as x goes to infinity. So instead of having to worry about doing crazy derivatives, we're going to compare them both to some easier function like x. And if they both grow at the same rate as that third function, so we're going to find h of x to just be x. So remember f of x and h of x, g of x and h of x. So let's see here. So the limit as x approaches infinity of f of x over h of x is the limit as x approaches infinity of the square root of x squared plus 5 over x. So we can actually move this guy back underneath the root if we square him. And then, so what I'm doing is I'm going to do this. So it's going to look like this. So now the whole thing's underneath the root. And if I do that, I can rewrite it like this. So as x goes to infinity, this becomes 0, so I get root 1. So this is all 1. And so let's see here. We'll do the other one. So the limit is x approaches infinity of g of x over h of x. So that's the limit of 2 root x minus 1 quantity squared all over x. So let's see here. If I want to put this guy inside the quantity, 2 root x minus 1 over root x squared. So now if I square down there, so this is going to become the limit. So this would be, so break it up into two terms. So 2 root x over x would just be 2 minus 1 over root x squared. So if x goes to infinity, this goes to 0, this whole thing goes to 4. So if we really want to work this out, so they both grow to numbers, so they grow at the same rate. But if you want to do this, you do the limit of f over g times g over h. Nope, no, that's wrong. Did that wrong. F over h times h over g. So f over h was right here. This is 1. H over g is the reciprocal of this, so 1/4. So you get a number, so they grow at the same rate. And that is the end of the section.